Welcome everyone. This is my presentation on applying the Cayley-Hamilton theorem in solving some problems. I've taken the Cayley-Hamilton theorem here from the textbook Linear Algebra by Fredberg and others. Now the Cayley-Hamilton theorem states let T be a linear operator on a finite dimensional vector space V and let Ft be the characteristic polynomial of T. Now, when you input t into your characteristic polynomial, what you will have is a zero matrix. Your output will be the zero matrix. Now, what happens here is that t satisfies the characteristic equation. You use t and you put your matrix into the characteristic equation. You'll see your result will be zero. Now, I will use this principle here stated by the Cayley-Hamilton theorem to help me solve two problems here, right? And what I want to do exactly is to use a matrix E, right? Given this matrix A here, I'm going to write a linear combination, right? I'm going to use linear combinations with this matrix here A and the identity matrix to arrive at A inverse and A squared. The Cayley-Hamilton theorem provides a nice framework in solving problems like these. So right away, looking at the theorem here, what we want to do, we want to get the characteristic polynomial of our t here, which happens to be this matrix here, A2621. And that's the first thing we'll do. We'll go ahead and get our characteristic polynomial. And you'll see how the Cayley-Hamilton theorem really provides a neat framework, as I said, in solving problems like these here. So onward to the characteristic polynomial. Now, I stated my method here in finding the characteristic polynomial of A. And you can see I've used the determinant method. Now, what I did is that I look at the leading diagonal 2, 1, and I say t minus 2 and t minus 1. And for the non-leading diagonal 2, 6, I change their signs. So positive 2 becomes negative 2, and positive 6 becomes negative 6. And then I multiply t minus 2 by t minus 1, and of course subtracting negative 2 times negative 6. And the resulting characteristic polynomial is t squared minus 3t minus 10. Now, according to the principle here spelled out by, given by the Cayley-Hamilton theorem, is that when we input our matrix into the characteristic polynomial, what we'll get is the zero transformation, we'll get 0. So wherever we see t here, we will input our matrix E. And for the constant 10 at the back here, what we'll attach to it, we'll use 10 as being the coefficient for the identity matrix, right? So we're coming along neatly here in applying the principle of the Cayley-Hamilton theorem in finding A inverse and A squared. So let's see what other steps we'll reach up here next. So we have to know what we have to do next is to state that P of A is equal to 0. Or basically, when we substitute A, as I said before, into a characteristic polynomial, we have 0. Okay? And you'll see that that is stated here. That is stated right here. Now, t squared, I substitute A there, I have A squared minus 3t. I put A there. And I've said I'll use 10 as a coefficient for the identity matrix, the constant 10. You always do that, right? Now, I will move on to now changing the subject of the formula because I want to make A squared the subject. And you see here that A squared is equal to 3A plus 10I. And I have worked that out here. A squared is equal to 3A, and A is 2621. Plus 10i, and of course that's the identity matrix. You work that out and you will see you'll get 16, 18, 6, 13. Now we have written A squared as a linear combination, right? As a linear combination of our matrix A. and we've utilized our identity matrix. And you see how the Cayley-Hamilton theorem comes in and saves the day in solving this problem. Okay, all right, let's just move on to the next part in solving the problem, which is to get A inverse. Now, what will happen again is that we will restate back what we would have gathered at the beginning of what A squared is equal to. So we'll restate the point that A squared is equal to 3A plus 10I. We restate that. And then what we will seek to do is to make I the subject of the formula. Now, I is equal to 1/10 of A squared minus 3A, right? And then the next step for us to do is to factor out an A, right? So we'll factor out an A here. You can see me doing that here. Okay. So A into 1/10 of A will cover for the first part here. Okay. And A into negative 3/10 I will cover for the second part at the back here. So I've now gotten that the identity is equal to A into 1/10, sorry, 1/10 of A, yes, A into 1/10 of A minus 3/10 of I, right? That is what I is equal to. It's equal to this part here. Now, since we gotten that I is equal to A times all of this here in the bracket, 1/10 of A minus 3/10 of I, we can see clearly that in the bracket there is A inverse. So substituting the value of A again, we'll come up with our A inverse value. So substituting values there for A, we have that A inverse is equal to 1/10 of A minus 3/10 of I. And you can see that clearly leading us to our answer here at the back. So this here is our answer. Good. So now we can move on to our second problem. Okay, so now we have a very similar problem as the one that we worked before. So basically what we want to do again is to use the matrix A, write linear combinations of that and the identity matrix to arrive at A inverse and A to the 4th power. Okay? So we will utilize again the principle stated in the Cayley-Hamilton theorem, whereby we will come up with our characteristic polynomial. And then for the variable in the characteristic polynomial, we'll substitute the matrix itself, A. And that will lead us to the transformation 0. We'll get 0 as our output, right? So you notice here my method in finding the characteristic polynomial for A. I've simply looked at the leading diagonal, which is -3, -7, and I say t plus 3 and t plus 7. And for the non-leading diagonal, what I did for -1, 8, I changed the sign. So -1 becomes +1, and +8, yes, I'm doing the correct thing. +8 becomes -8. And of course, multiplying t plus 3 times t plus 7 minus the product of 1 and -8. Good. So t plus 3 and t plus 7 minus -8 will lead us to this characteristic polynomial here, t squared plus 10t plus 29. So by the Cayley-Hamilton theorem, we have that p of A is equal to 0. So wherever we're seeing t here in our characteristic polynomial, we just input, we substitute the matrix A, and we'll see our solution. We'll see our solution is equal to 0. Good. So moving on now, what we have P of A is equal to A squared plus 10A plus 29I. And that, of course, by the Cayley-Hamilton theorem is equal to 0. Now, this will help us to make A squared the subject. And A squared is equal to -10A minus 29I, right? But the thing is, we don't want A squared. We want A4. That is what we want, A to the 4th power. But we can use a squared to get to a to the 4 because we can multiply in this here, in this equation here that we got. What we can do, we can multiply a by a on both sides. Now when we do that, we'll have a cubed, and you'll have negative 10a squared minus 29a. Now the thing is, we know what the value of a squared is. We know that the value of a squared is negative 10a, negative 10a minus 29i. Good. So I'm going to substitute that into a cube here. And what I'm going to get is, I'm going to get this here. I'm going to get negative 10 into negative 10a minus 29i minus 29a. And that will lead me to a cube is equal to 71a plus 290i after simplifying. Now I'm still not finished. I need a to the 4th. I'm now at a to the 3rd currently. So what I'm going to do next, I'm going to multiply both sides by a. And that will lead me to 71a squared plus 298. Okay? So yet I have to do some more simplification, substituting and simplifying, because I know that the value of a square is stated right here. I have it here, that the value of a square is equal to negative 10a minus 29i. So I'm going to substitute it for a here, and I'm going to see what I will get. Okay, let us see what will happen. So coming down here, you see that when I do this substitution, I have 71 into negative 10a minus 29i, and bringing down the what is at the back there, 290a. And simplifying that, I'll have a to the 4th is equal to 490, negative 490a. I have negative 490a minus 2059, sorry, I. Now I will just have to substitute the value of a here and the value of I, do the necessary simplification, and you see the answer is this here. Okay, we'll verify that. You can use a software on a computer to see that your answer is that. You can use a calculator, right? You can use a calculator to find that that is the answer. Good. Now moving on to the other part, we want to find a inverse, and I'm going to restate back the value of a squared, the formula for a squared. I'm going to restate that back, and I'm going to work from that there after restating it, because a squared now, a squared is equal to negative 10a minus 29i, and I make I the subject. That will lead me to I is equal to negative 1 over 29 into a squared plus 10a. And I factor out a, and a into negative 129, a will cover for the first part at it here, and a into negative 10 over 29i will cover for the part at the back here. Good. So I now a into what I have in the bracket here, a into this term here gives me the identity, and that means that what I have in the bracket here is the inverse of a. So I stated that a inverse is equal to 1 over 29 of the value of a minus 10 over the value of the identity, and that leads me to this answer here, and that's it. So you would have seen how the Cayley-Hamilton theorem provides a very unique approach. I find it that is a neat approach. I like it, and I hope you enjoyed the video. Thank you very much for listening. All right, then take care.